Welcome back to the NMR Challenges series. In the previous video, I provided this NMR challenge for you. And today, we are going to explain the solution step by step. If you have already solved it, then you can match your answer by the end of this video. So let's start today's NMR challenge.
So this is our 8th NMR challenge in which we are going to determine the structure of the compound having molecular formula 66H10O2 from the given 1H NMR and 13C NMR. And this problem is very interesting because it is not easy to determine the structure of this compound. So while determining the structure of this organic compound, we are going to follow all those steps which we learned in the last videos. So first we will calculate the index of hydrogen deficiency, then we will look 1H NMR, and after that we will look 13C APT NMR. Before solving this problem, we are going to revise all those steps which we are learning since beginning, and we will revise chemical shift value for 1H NMR and 13C carbon NMR as well. This is very important to keep revising because this practice will make you perfect. And here are those steps. So first step is calculating the index of hydrogen deficiency, which is also known as degree of unsaturation, and this is the formula. So this formula is 2 multiplied by number of carbon atoms plus 2 plus number of nitrogen atoms minus number of hydrogen atoms minus number of halogen atoms divided by 2. So the value gives number of pi bonds or rings, or it could be both. If this value is equal to 5 or greater than 5, then we can blindly say that it has one benzene ring, and this benzene ring will correspond to the 4 value because it has 3 pi bonds plus 1 ring. Then we will see 1H NMR, and as we said that number of signals is equal to the how many types of protons are there. Splitting patterns will give us information about the number of neighboring protons or substitution pattern on the benzene ring. So here is the splitting pattern formula, n plus 1, where n is equal to the number of adjacent protons which are equivalent. And for determining the substitution pattern on the benzene ring, we should also know the J coupling value. So we will learn when we will have those kind of problem. And 1H NMR chemical shift values is also very important to understand shielding and deshielding of the protons. As I told you, primary carbons, hydrogens coming in the shielded region from 1 ppm to 1.2 ppm. Secondary carbon hydrogens are slightly deshielded as compared to the primary, and tertiary hydrogens are slightly more deshielded from 1.4 ppm to 1.9 ppm. And we also learned that when methyl is attached to the ketone, then it comes from 2 ppm to 2.6 ppm, and it is quite similar value for methyl attached to the benzene ring, such as in toluene. So it is also coming in the same region. Acetylene protons is slightly deshielded as compared to the methyl attached to the aromatic rings. It comes from 2.5 to 3 ppm. This is very interesting value. When oxygen attached to the carbon, then hydrogens are coming around 3.5 to 4.5 ppm more often, and it could be higher also, but usually you will see in this range. And when it is attached to the nitrogen, then it can come from 3 to 4 ppm. We also learned that hydroxy and amines protons are acidic, therefore they can undergo exchange from one molecule to another molecule, therefore their values are not fixed, and it is coming from 1 to 5 ppm. The aromatic protons comes from 6 ppm to 8.5 ppm, sometimes overlap with the alkene protons. This depends on the nature of the alkenes. Aldehyde protons comes from 9.5 ppm to 10.5 ppm, but carboxylic protons always comes after 10 ppm to 13 ppm, and it is slightly broader signal. So we should remember these values because it is very important to determine the structure of the compounds. Then the third step is 13C APT NMR. So we will look 13C APT NMR, and we know that this NMR gives all kind of carbon signal, but in 13C depth NMR we don't see signal for quaternary carbon, the carbon which doesn't have any hydrogen. It also tells us how many types of carbons are present in a molecule. And we also learned that methane and methyl peaks are 180 degree opposite to quaternary carbon and methylene carbon. So in this spectra which we are going to show here, the quaternary carbon and CH2 signals coming in the upward direction, or we can say in a positive phase, and methane and methyl carbon are coming in the negative phase. But remember that when you are solving in MNOVA or any other software, then you can change it. You can change this phase by yourself, and then it could be opposite. But here the NMR which we are looking, in that case we are following this pattern because those NMRs are presented in this way. It is also important to remember some of the chemical shift values for carbon. So here are some chemical shift value for the carbon. When it is primary, So it is coming up to 35 ppm. When it is secondary, it is slightly deshielded. Tertiary is coming maximum 55 ppm. When it is connected to the oxygen, then it comes from 50 to 70 ppm more often, but it could go to 90 ppm depending upon the structure. Acetylene carbon comes from 70 to 90 ppm, and benzene carbons comes from 110 to 170. These values for the functional groups is very important to remember. Ester comes from 165 to 175 ppm, but amides could be slightly lower than ester. It can be from 160 to 175 ppm. Carboxylic acid is slightly higher from 175 to 185 ppm. Aldehyde always coming in highly deshielded region from 190 to 200. Therefore, it is easy to distinguish between carbonyl carbon from ester or carboxylic acids. Okay, so after revising the chemical shift value, we are ready to take this challenge. So first, we are going to determine the index of hydrogen deficiency by using the formula 2C plus 2 plus nitrogen minus hydrogen minus halogen divided by 2. So it will be 2 multiplied by number of carbons are 6 plus 2 plus nitrogen 0 minus 10 hydrogens minus there is no halogen. So divided by 2. So it has 2 degree of unsaturation, and this could be either 2 pi bonds or it can be 1 pi bond plus 1 ring, because 2 ring possibility is very less. So I am thinking it can be 1 pi bond and 1 ring. Now we are going to check the 1H NMR, and as I told you, first we will see how many signals are there. So there are 2 signals. One, this is, let's say, A, this is B. So there are 2 signals, means there are 2 types of protons. There are 2 types of hydrogens, and now the signal A is at 2.18 ppm, which has integration value 3 hydrogen, and it is singlet. So this implies that the n value will be 0, or it can be like a equivalent hydrogen in the neighbor. In neighbor there could be equivalent hydrogens, or there is no hydrogen, and these 3 hydrogens indicates that there is a CH3 group. Now if you look at this value, we remember that this value indicates that CH3 is attached to either carbonyl group, or it is directly attached to the benzene ring. But for the benzene ring, we must see the signal for the aromatic regions, but there is no signal in the aromatic region. This is CdCl3 is the deuterated solvent signal, and there is no aromatic signal, so the possibility of this is 0. So methyl probably attached to the keto group. Okay, let's see further. Now if you see that signal B is at 2.70 ppm, and this is also singlet, right? Its integration value is 2 hydrogen, singlet. So this indicates that N is 0, or there are equivalent hydrogens, means same hydrogens, right? And this value indicates that there is a CH2, and this value probably saying that this is also attached to the keto group. So let's see the carbon NMR, because at this, from the 1H NMR we can't conclude anything. Now from the carbon NMR, if you see that in the 13C APT NMR there are 3 carbon signals, right? So this indicates that there are 3 types of carbon, but if you see the molecular structure, there are 6 carbons, right? So it means the molecule has symmetry, and 3 carbons are equivalent to other. Now we know that upward signals belongs to carbon or CH2, and downward signals belongs to CH3 or CH. Now there is a downward signal, and we have already confirmed that there is a methyl, so this probably belongs to the CH3, and this one belongs to CH2. Okay, this is clear to us. Now look at in the deshielded region, there is a signal with low intensity, and we have already learned that this could be belongs to aldehyde, because it is around 200, because after 200 it is usually belongs to the carbonyl of ketone or aldehyde. But in the 1H NMR, we don't see signal for the aldehyde. So therefore, this is not possible that the compound have aldehyde group. So what is possibility is that it has keto group. Now we have following information that the compound have keto group, CH3 group and CH2. Okay, let's go back and if you see that when we were calculating the hydrogens, so this is 3 hydrogens and 2 hydrogens, so total 5 hydrogens. But in the compound there are 10 hydrogens. It means we have to multiply by 2, and this is the ratio of the NMR integration value, and if you multiply then it will be 10 hydrogens. So it's directly saying that there are 2 equivalent of CH2 group and 2 equivalent of methyl group. I hope it is clear. So there are 2 CH2 which are same and 2 methyl which are same. Now what is left? Okay, now number of hydrogens are full because this is will give you 6 hydrogens, this will give you 4 hydrogens, and 4 carbons, this is 2 carbons from here, 2 carbons from here. So how many carbons? Total 4 carbons. Now what is left? 2 carbons left. So it means there are 2 keto group in the molecules. This is keto group and this is identical, that's why it is showing at one signal, not 2 signals. Okay, now let's draw all the possibilities. So we understand that there are 2 similar keto group. So molecule has plane of symmetry. So I am thinking maybe the structure could be like this. So this CH2 is attached and then CH3, then CH2, then CH3. But this is not the correct structure because there are 2 reasons. First reason is that this CH2 must show quadrate, right? Because of n plus 1 rule, it has 3 in the neighboring, and this methyl will show triplet. But what we are seeing? We are seeing only singlet for both, right? And this molecule has plane of symmetry. So this is A type, this is A type, this is B type, this is B type. This is okay. But this splitting pattern showing that this cannot be the correct structure. And there is another reason. If you remember, we have already concluded that this methyl is attached to the keto group because of the 2.8 ppm value, right? So this is not correct at all. Now we have to think what could be other possibility. So other possibility is that, let's say we can put CH2, let's put CH3. Okay, this is we have already concluded. Now CH2 and CH2. Now these two CH2 are equivalent, right? If we put keto group here and then methyl. So now we can say that this is A type, this is A type, and this is B, and this is also B. So, and if you pass the plane, you can divide this molecule into 2 identical half. So how many carbon signals? So 1 carbon signal for this keto group, 1 for this second, and 1 for methyl. And this is our satisfying our carbon NMR. Let's look the proton. So this is belongs to A methyl, and this signal belongs to B type of proton, right? And the value is also showing that the CH2 is attached to keto and CH3 is also attached to the keto, and there are identical protons. Therefore there is no splitting in this case, because as I said that there is a possibility N0 or N or equivalent hydrogens, right? So there are equivalent hydrogens, same hydrogen, so no splitting. So it will show you singlet, CH2 singlet, right? And methyl of course singlet because there is no neighboring hydrogen. So this is the correct structure of this compound. I really like this kind of NMR challenges and it was very interesting challenge for me. Now in the next video we are going to determine the structure of this compound, and this is the 1H NMR and this is the carbon 13C NMR. If you are interested, you can solve and let me know the answer in the comment box. Anyway, we are going to solve in the next video. So don't forget to subscribe my channel. We will see you in the next video. Thank you very much. Take care. Bye bye.